Hello viewers, welcome you all. In today's lecture, I am going to take up some other topics from high energy physics, right, or particle physics, right. In the earlier lectures, I have covered basic properties of elementary particles, their classification, right, different interactions, fundamental forces, then quark model. Now there are two topics which are left, and question can be asked from these topics. The first one is deuteron, right? Right, deuteron, right? So usually, question is asked from the properties of a deuteron, right? It can be related to its spin, right? Parity, isotopic spin, right? About the ground state, its quadrupole moment, magnetic dipole moment, right? So, what is deuteron, right? So, deuteron basically is a combination of a neutron and a proton, right? This combination, when the neutron and proton join together, this combination is known as a deuteron, right? Uh, we know very well that hydrogen can have three isotopes, one H1, one H2, and one H3. So protium, deuterium, tritium. Deuterium Deuterium have one neutron plus one proton in the nucleus, and one electron is revolving around the nucleus, right? It has only one proton. It has uh, two neutrons and one proton, right? So this is the case of these three isotopes, but I'm interested in this one, deuterium. So if I have deuterium atom and I remove the electron from that, then I'm left with only the nucleus of deuterium. That is known as a deuteron, right? Neutron, and it is a combination, as I told you, of neutron plus a proton, right? Neutron and proton are joined together by strong nuclear forces, right? So when the different properties of deuteron, it is usually represented as symbol either by small d or capital D in nuclear reactions, right? So, as I told you that when we found different properties of the deuteron by different, experiments, it is found that the deuteron exists with spin I is equal to 1. It means we know very well that the spin of neutron and proton is both half. It means both of these particles have their spins parallel, right? That's why 1 by 2 plus 1 by 2, that will give you 1, right? So when these two nucleons, join inside the nucleus, they are in the spin parallel state, right? Uh, if I talk about the orbital angular momentum L, then it is found that it is equal to 0, and the total angular momentum, or we call it as total spin, right, of this state, then it is obviously equal to 1, right, because it is equal to spin angular momentum plus orbital angular momentum, right? So it is equal to 1, right? As far as the parity of the deuteron is concerned, it is found that it has a even parity. Even parity means it is a plus 1, right? We know very well about the parity, and in fact I am going to take parity in this lecture also. So it has even parity. As far as the winding energy, right, of deuteron is concerned, it is found that it has winding energy approximately 2.24 mega electron volt, right? We know very well that the average winding energy of all the nuclei is around 8 mega electron volt. So this means this energy is very, very less, as compared to this energy, right? It is very, very small. So we can say that deuteron is a very loosely wound state, right? So as the binding energy, as I told you, it is very, very small. So usually deuteron is found in the ground state, and excited states are rarely to exist, right? As far as the magnetic dipole moment, right? We know magnetic dipole moment mu of deuteron, it should be equal to magnetic dipole moment of neutron plus magnetic dipole moment of proton. We know very well about the magnetic dipole moments of proton and neutron. It is when we put the value plus 2.7927, and for neutron it is minus 1.9131. If I add up these two, I will find approximately value 0.8796, right? But when we found the magnetic dipole moment of deuteron, it is found that it has value approximately 8.8573. So it means these two values are not equal, right? So this is very, very important result, right? It means the actual magnetic dipole moment of the deuteron is not exactly equal to the sum of the magnetic dipole moment of its constituent particles, right? So then this feature of the deuteron reveals many property about the nuclear forces, right? So I'm not going into all details of that, but we have to remember that the magnetic dipole moment of the deuteron is not exactly equal to the magnetic dipole moment of neutron and proton. If we talk about the quadrupole moment, then quadrupole moment again for the deuteron is not equal to 0, right? But it is found that it has some positive value, right, of the order of 0.29 femtometer square, right, in terms of multiplied by the electronic charge, right? So if it is positive, it means the deuteron that is formed by the combination of neutron and proton is not spherically symmetric, but it has a shape of a prolate spheroid. I have explained about the electric quadrupole moment of the nucleus in another lecture, so you can refer to that. So here we have to remember that quadrupole moment is not equal to 0, and it is we can say having prolate spheroid shape, right? Now, if I come to the states of the deuteron, then it is found that this deuteron exists as a mixture of 3s1 plus 3d1 states, right? We know these are the spectroscopic terms for these uh, uh, different states of the two nucleons, right, for the different combinations of L, S and J, three quantum numbers, right? Here this S corresponds to the value of L, this 3 corresponds to 2 small s plus 1, right, and this 1 corresponds to the value of J, right? So it is found that this deuteron exists in as a mixture of these 3s1 and plus 3d1, right? Here 3 3 means 2s plus 1 is equal to 3, it means s is equal to 1. So as I told you that the spin of the deuteron is plus 1, here I told you in the beginning, it means it is the triplet state, right? It is in the triplet, right? Triplet state, right? We call it as a triplet states, and the spins are parallel, right? The spins of the constituent particles are parallel. I also told you about the isotopic spin, right? I think I didn't told you about the isotopic spin. So as far as the isotopic spin, I am representing it as T here, right? It is found that the isotopic spin of deuteron is equal to 0, right? So we have to remember it, because in some nuclear reactions isotopic spin can be used there, because you can be given a deuteron involved in that nuclear reaction. So these are some properties that we have to kept in mind while dealing with the problems related to the deuteron. So as I told you, deuteron is simply the nucleus of deuterium, right? That is an isotope of hydrogen, right? That contain one neutron, one proton, and if we remove add electron to that, then it will become deuterium, right? So this is about some properties of neutron. Now I am coming to the second topic, that is symmetry operators. Symmetry operators or operations in particle physics. So in particle physics, we mainly comes across three symmetry operators, right? The first one is a parity operator. Second one is a charge conjugation, right? Uh, Third one is a time reversal. Right. So these are three symmetry operators that are commonly used and discussed in the high energy physics or particle physics. So as far as parity is concerned, we know the operation of parity on a system, change the, reverse the signs of all the coordinates. I can say if I operate parity operator on a wave function that is r, then it simply means that we are changing all these r2 minus r. Now when these all the coordinates are changed, if the wave function remain as it is equal to psi r, right, then we call the system have a even parity or positive parity, right? But if it becomes negative of psi r, the system changes its sign, then we call it as odd parity or negative parity. So we have learned all these things in nuclear physics. So this is about the parity operation. Now as far as parity operation is concerned, usually it is asked that parity is conserved in which fundamental interaction. So as far as the invariance or conservation of parity is concerned, it is found that parity is conserved in strong as well as electromagnetic interactions, but it is violated in weak interactions. It is not conserved in weak interactions, particularly in beta decay, right? So we have to remember it, and how we change apply the parity operator on a system. We can apply parity operator on any system. For example, suppose I am applying parity operator on a linear momentum, and it is if I take it simply, it is m into v, right? Now m into v, velocity is what? It is m into dr upon dt, right? So if I'm changing the sign of r, obviously momentum will change its sign. So this is the way of applying this parity operator on a different physical quantity, or we can apply it on a physical equation, right? Now I'm coming to the second one, right? That is charge conjugation, right? Now charge conjugation is again a symmetry operation, and I am representing it as this one, C cap. Now charge conjugation means nature makes no difference between the particles and antiparticles. If in reaction, nuclear reaction or a reaction of elementary particle, I replace each particle by its antiparticle, then that nuclear reaction should exist in the nature with equal probability. If that thing is happening, it means charge conjugation is conserved in that interaction. But if it is not happening, then it is violated. Suppose I am applying charge conjugation of a proton plus pi negative, that gives you sigma negative plus k positive nuclear reaction. So it will change this into antiproton plus, right, pi positive, that gives you this one negative plus k negative. So you can see here, now each particle is replaced with its corresponding anti-particle, and this reaction, the resultant reaction, should have equal probability, right? This is simple meaning of charge conjugation invariance. Charge conjugation invariance means the nature shows no preference for particles over their anti-particles, right? Interaction and process remain unchanged if the particle is replaced by its antiparticle. Now if we talk about the conservation of charge conjugation in different fundamental interactions, then again it is conserved in a strong and electromagnetic interaction, but it is violated in a weak interactions, right? So this is the case of charge conjugation, and it is represented by C operator. Now I am coming to the last one, that is time reversal. Now time reversal, it is represented as a T operator. Now time reversal operator means if I apply this operator on a system, then the time in that system will get reversed. For example, again let's take the case of momentum, right? P is equal to m into b, right? If I simply write it, then I can write m into d x upon dt. I am writing x here. Now if I apply time reversal operator on this linear momentum, then it will change, because here time will become minus t, right? So m dx upon d minus t, right? Sorry, it is minus t, right? So in that case, this minus will be taken outside, so it will give me minus dx upon dt. So you can see here the sign of the physical quantity, and that is linear momentum, is changed, right? So this is the way of applying this time reversal operator, right? Time reversal simply means if the process is proceeding forward in the time, and if I reverse the direction of the time, right, then according to the conservation or invariance of time uh, you know reversal operation, the process or phenomenon that will take place with equal probability. If that thing is happening, then we can say time reversal operation is conserved. But if it is not happening, right, the system is changing its sign, it means time reversal is violated, right? So now again, if I come to the uh, its conservation in different fundamental interactions, then as far as strong and electromagnetic interactions are concerned, it is conserved. But again, it is violated in weak interactions, right? As far as gravitational force is concerned, I'm omitting this from the discussion. We don't know exactly about it, right? It is the most confusing force in the nature. Until now we don't have any quantum theory for that can tell us all the things related to the gravitational force, right? But all the things that I discussed here, they has been experimentally verified, right? So this is about the three symmetry operations in nuclear and particle physics and their corresponding conservation laws, right? So parity, charge conjugation, and time reversal, right? Now there is an important theorem related to these three symmetry operations, that is parity and charge conjugation and time reversal. That theorem is known as a CPT theorem, right? CPT theorem. This CPT theorem in particle physics or high energy physics states that all the process in the nature are invariant under the combined operation of CPT. It means if I apply C operator, parity operator, and time operator on any process in the nature, right, then that process will remain invariant. Invariant means it will remain as it is, it will not change. This is CPT theorem. Here it doesn't matter that we are taking C earlier, T later, right? If I write it in the form of PCT, then it is equally valid. If I write it as a CTP, then again CTP, then again equally valid, right? But for convenience, we are calling it as a CPT theorem, right? It means when the combined operation of all three symmetry operators is applied on a process in the nature, then that process remain invariant. It doesn't change, its sign, or we can say it is not violating the these three symmetry operations. Any of these three symmetry operations, right? So this is CPT theorem, right? Now I'm going to take up some questions that are asked from these symmetry operations in particle physics, right? So I'm coming to the first question, that is, you can see here, the question is, you can see, if E and V, right, are electric and magnetic field respectively, right, then E dot V, right, is odd under parity and even under time reversal. Different options are given. I mean, we have to check that what is this quantity when we apply parity operation and time reversal operation on this term, right? So for it, we know very well if I apply parity operation on electric field, right? Then we have to recall that it remain unchanged E. But when I apply parity operation on magnetic field, then it reverse its sign. So it is minus V, right? Similarly, if I apply time reversal operator on electric field, right, then it changes its sign, right? E, it becomes E. What if I apply time reversal operator on magnetic field, right? All these are vectors, right? Here you can suppose that these are vectors, right? So when I applied on it, it does not change its sign. So you can see in either case, right, whether if E is a parity operation is applied on E and this, then in that case I will have in all the cases E dot V is always a negative, because you can see here, right, parity operation on E, it leaves E, right, then parity operation on V, it changes sign. So when I take the dot product, that will obviously change its sign. Similarly, when I apply time reversal operation on E, it changes sign, but B doesn't changes, but the dot product will change. It means both parity as well as time reversal will be odd, right? So I think odd under parity and odd under time reversal. This is the correct answer, right? So these type of questions are usually asked related to the symmetry operations. Now I am coming to one more question. So you can see these questions are from GATE exams. You can see under parity and time reversal transformations, again same thing, which of the following statement is true about electric dipole moment P and magnetic dipole moment mu, right? So we know very well as far as electric dipole moment, right, they are taking P is odd under parity and mu is under time reversal. I mean, they are applying parity operation on linear momentum. I am writing it as it is, right, whereas they are applying time reversal operation on this, right, magnetic dipole moment mu, right? Now as far as this linear momentum is concerned, we know very well when we apply parity operation on the linear momentum, it changes its sign, right, because P is equal to m into B. So I have explained earlier in this lecture. So it becomes minus, right? So it means for linear momentum the parity is odd, right? Now what about magnetic dipole moment? So we know it is magnetic dipole moment, we usually express it as EH cat upon 2m, right, into angular momentum L or S, right? Now here, this is angular momentum L. L is equal to R cross P. I can write E H cut upon 2m into MBR. So B is again taking dx upon dt or dr upon dt. So when I will take time reversal, it will change its sign. It means that magnetic dipole moment will also change its sign under time reversal, because you can see here dx upon dt. T is negative, it will be taken outside, it will change the sign of a magnetic dipole moment. So it means both linear momentum as well as a magnetic dipole moment have P has odd parity, right? And where is the option? I think this is P is odd under parity and mu is odd under time reversal. So this is the correct answer, right? So again, same kind of question was there, but the one thing that I want to tell you, that we have to remember the parity, time reversal, and charge conjugation operations for important physical quantities like electric field, magnetic field, electric dipole moment, magnetic dipole moment, linear momentum, angular momentum, total isospin. So if we remember their properties under parity, charge conjugation, and time reversal, then we can solve this type of problems, right? Now I'm coming to the next question. You can see here that let let S and P represent spin and again linear momentum of elementary particle under time reversal operation T. Spin and linear momentum. We know very well that linear momentum is changed under time reversal, right? So obviously these two options are not changing the sign of linear momentum, right? This is the operation on the linear momentum, time reversal operation, but it is remaining the same. Option dropped, option dropped. It can be this one, it can be this one. Now what about spin, right? Spin angular momentum, right? S is spin angular momentum, where P is a linear momentum. So as I told you that linear momentum changes sign, so these two options can be there. But now I am looking at the this spin, right? This one, right? Then under time reversal, right? When we apply this on spin, I mean this operation. So whether the spin will change its sign or not. So it is found that it also changes its sign, right? So it means this option. Option number B is the correct answer. Both spin, angular momentum as well as linear momentum changes its sign when we apply time reversal operation on it, right? So correct answer is this one. So again same type of question, but I repeated that we have to remember the properties of different physical quantities and three symmetry operations, because usually question is asked from these type of problems, right? In the according to this problem that I solved here. So this is about these three problems that I discussed, that are based on this entire discussion that we have done in this lecture. So sometimes questions are asked from here or from the Deuteron. So I have also covered it here. I'm hopeful that the things are very clear now. So thank you very much.